The average speed of traffic on a road between 6 a.m. and 10 a.m. on a representative day is modeled by this, where f of t is measured in miles per hour. Whew, good. This felt like that should be measured in feet per second, probably because of the function of t thing. Which time is traffic flow the lowest? So we're looking for a minimum. Okay. Interesting. Wonder what happens. How fast is that? So we plug in 6, we get 0, 0, 50. Oh. Okay. Ooh, maybe I should know that. I'll write that down. So traffic at time 0, f of 0 equals 50. F of 10 equals, let's see here, 20 times 4, so that's 80, minus 40 times 10 minus 4. 10 minus 6 is 4, square root is 2, so that's also 80, plus 50. So it starts at 50 and ends at 50. Interesting. Interesting. Okay. So to optimize things, we're going to find a maximum and or minimum. I guess in this case a minimum. Slowest. Lowest. Ooh. Slowest and lowest. Those are surprisingly similar words. 20 times t minus 6. Okay. Okay. So this first term will just be, actually, it'll be 20, but I want to write it out a little bit more. So this is going to be 20t minus 120. No. Yeah, minus 120. And so the 120 will go away. And you'll be left with 20. The other way of looking at it is you can look at this as the chain rule. Not the chain rule. Chain rule? Yeah, power rule. And chain rule. So if this is t minus 6 to the first, the 1 comes down here, and then that becomes 0. Anything to the 0 is just 1. So what we'd be left with is 20 times 1 times the derivative of the interior, which would again be 1. So you can do the chain rule, power rule, or distribute, and get the answer that the derivative of 20 times t minus 6 is just going to be 20. And I'm going to rewrite this real quick. 40 t minus 6 to the 1/2. Okay? So then we'd add to that 1/2 times 40 times t minus 6 to the negative 1/2. And the 50 goes away. Okay? So I'm going to rewrite this real quick. This red is just so aggressive. 20 plus 20 over t minus 6 square rooted. Okay? I'm good with that. And this is the derivative. And we want to set this equal to 0 and solve. Is that even possible? Oh, because it's a negative. There we go. Whoop. That's just causing confusion up there. So negative 20 minus, yep, okay. So there's a negative. I'm going to set it equal to 0. And we're left with the situation of 20 equals 20 over t minus 6 square rooted. So we're left with t minus 6 square rooted equals 1. T minus 6 equals 1, since we square both sides. T equals 7. So the critical point is 7. So the only time when it would change would be at 7. So what we're going to do then is, since we know that the beginning and the end are the same, we're pretty sure, well, we want to test the endpoints. So like 6 a.m., 10 a.m. But since we know they can't, it's not an option for both of them, we're suspecting then that they will not be the answer, because we'd want to see 6 a.m. / 10 a.m. for both of them. So what I'm saying here is if it actually looks something like, if the traffic flow looked like this, where 7 a.m. is a maximum and not a minimum, because what we did was we just found a critical point, then we'd have to look at the endpoints. But if we just tested earlier that both 6 a.m. and 10 a.m. gives us 50 miles per hour, so then if 6 a.m. and 10 a.m. were both possibilities, we'd expect one of the answers to be 6 a.m. and 10 a.m. But since we have two possibilities there, we're pretty sure, just the way the question is set up, that 7 a.m. is going to be the answer. But being a good test taker type person with minimal trust, or trust issues, however you look at it, I'm going to test it anyway. So what I think is going to be something like this, where we have 50, 50, and 7 a.m., which is less. So f of 7, there we go, equals 20 times 7 minus 6, which is 1, minus 40 times the square root of 7 minus 1, 7 minus 6, which is 1, plus 50. This gives us 20 minus 40 plus 50. This gives us minus 20, which gives us 30. Aha! So 30 miles per hour is the slowest that things go, which happens at 7 a.m., which is our lowest traffic flow. And that's how I would approach this problem. So to back up slightly, just to kind of recap, we're trying to optimize things. Or de-optimize? I'm not sure what the opposite of optimization is. I should look that up. Antonym? So we find the derivative that gives us critical points, which is potential times for it to change. It doesn't always change, but it's at that point when we can have a minimum or maximum. Set equal to 0 to find the min or max, potential min or max, and that's how we found 7 a.m. From 7, we then plugged it back in, and we looked at the endpoint to when we started and when we ended, and then we looked at 7 a.m. and verified that it was less than the endpoints, therefore it was a minimum. We also could have found the second derivative and used the concavity, but in this case, not worth the effort. Okay, that is how we do this kind of optimization problem.